In today's video, we will be discussing a brief introduction to calculus. There are two major topics in calculus, differentiation and integration. Let's discuss differentiation first. Look at the graph under the word differentiation. Here we have a graph representing some quantity. It could be cost, it could be volumes, it could be distance, a position, whatever the case may be. Now, in previous math classes, we have been able to discuss average values. So, for instance, if I was to take 2 points on this curve and draw a line between those two curves, that would represent the average value of this curve on the interval from about 0 to 2.8. That would be the average value. Now, in calculus, we're able to find the rate of change at a particular value. Now, with the average value, we have 2 points on the curve, and we know how to calculate the slope of a line if we're given 2 points. So finding an average value is not very difficult to do. However, if we try to calculate the instantaneous rate of change at a particular point, say for instance when x equals 1, we have this tangent line to the graph, but we only have 1 point. So how are we going to determine the slope of that line since we only have 1 point? Well, calculus helps us get around that problem. Now take a look at what's happening with this tangent line. This tangent line represents the rate of change of that function at x equals 1. Notice if I drew a tangent line back here at about, well, let's say negative 1.2. If I drew this tangent line to the curve, I know it doesn't look quite tangent, but let's say that's a tangent line to the curve at that point. The slope of this line has a positive slope, where the slope of the line at x equals 1, this has a negative slope. So the rate of change back here has a positive rate of change. It's increasing, where at x equals 1, it has a negative rate of change, or it is decreasing. And you can see that any point that you choose on the graph, the rate of change is changing. So at x equals 1, the rate of change is negative. So let's just say, for instance, the slope of that line is negative 3, let's say. Well, if I find the slope of the tangent line out here at 3.5, the slope of that tangent line is much more negative. It could be 10, it could be negative 12. So that's an important concept in calculus. We're going to be able to find the rate of change of a function at a particular instant. And that has a lot of different applications. As I was speaking of earlier, cost. If this represents a cost function, if the blue line represents the cost for producing some widget in manufacturing, we can see what's happening with the cost at any production level. Or if it represented the volume of, let's say, water coming into a lake, well, if we can measure the rate of change of the water, we can measure how fast it is coming in. What's the volume rate of change? We could describe distances or a position. If you have a position graph, if you look at the slope of a tangent line to a position curve, you can determine how fast the particle or a person or car or whatever, how fast it is moving at any instant. So those are some of the concepts that we'll be looking at in differentiation. Now, integration, the overarching concept is finding the area under a curve. So here we have a curve f of x. If we wanted to find the area under the curve from x equals a to x equals b, we can use integration to find that area. Now, this has a lot of different applications. This has to do with finding velocities, acceleration. In calculus, we look at finding how much work is done, the center of mass. You can determine kinetic energy. So there's a variety of different applications for integration. And these concepts lead us even into a more powerful tool, which is called differential equations. Now, that's another class you can take, but it's a very powerful tool to solve some very interesting real-world problems. So, let's get started. To help us with our study of differential calculus, we're going to be looking at the slope of those tangent lines that I drew on the last slide. Also, another intuitive idea that goes along with the tangent line to help us understand it a little bit better is we're going to be looking at the study of a velocity function and the velocity curve. So let's take a look at this problem here. Find an equation of the line tangent to the parabola y equals x squared at the point 1, 1. So here's the graph of x squared. We are asked to find the slope of this tangent line at this particular point. Now, in prior math classes, we've been able to find the slope of a line if we have 2 points on that line. We only have 1 point on this particular line. So how can we find this slope? We could actually estimate another point on this line and then calculate the slope of that line. So if we have another point, let's say we had this point right here, then we would have 2 points. We'd have an x sub 1, a y sub 1, an x sub 2, and a y sub 2. Then we could use the slope formula. We know the slope formula is m equals y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Now, the numerator in this formula here, this y sub 2 minus y sub 1, that's the change in the y value, and the x sub 2 minus the x sub 1 is the change in the x values. Like I said in the last slide, we could choose another point on the line and then use the slope formula to find the slope of that line. But we'd be estimating, if we chose a point out here on the line someplace else, we'd be estimating what that point would be, because we don't have the equation of the line, so we don't have an x value that we could plug into this equation of the line to find the y value. We'd just be estimating. What we're going to do is we're going to choose a point on the graph of y equals x squared, because we know we could find the actual y value for any given x value. So if we chose the point 2 when x equals 2, here we can see now we could calculate the slope of this red line. This red line is called a secant line. The black line is called a tangent line. A tangent line to a graph touches the graph at only 1 point, where this secant line is going to go through the graph twice. Now, the tangent line, I said, is only going to touch the graph at that 1 point. On down the line, it could cross the graph again, but we're talking about at a particular point. It's only going to touch the graph at this one particular point. We can now calculate the slope of our secant line, the red line. We can use our slope formula. We would plug in our values. There's our y sub 2 minus our y sub 1. minus 1 in the numerator, and then our x of 2 is 2, and our x of 1 is 1. So we have our 2 minus 1. And we can see the slope of that secant line is 3. So we're calling this the secant line. And this is our tangent line. We are interested in finding the slope of this tangent line. We are going to use a secant line to help us get there. We used the slope of that secant line in the last video. We could estimate the slope of our tangent line. We said the slope of that secant line was 3. What if we didn't feel that was a very good approximation to the slope of the tangent line? What if we moved our point a little bit closer to 1, 1 on the graph of x squared? So if we move that point a little bit closer to 1, 1, you can see we could now again calculate the slope of that secant line, and the slope of that secant line seems to be a little bit better than the last approximation. So again, we're going to use our slope formula, so we'll plug in our values, and now here for this graph, we chose the point 1.5. Last time we chose this point out here at 2, and we calculated the y value. We're doing the same thing here. We're taking our x value, 1.5, we're plugging it into this graph here is represented by y equals x squared. So we're simply taking the x value, plugging it in, and squaring it. So we have 1.5 squared, which is the y value, 2.25. So there's our x value, 1.5, and this y value would be 2.25. And then we calculate the slope of this secant line here, and we get a slope of 2.5. We can see that's a little bit better approximation than using x equals 2. You can see the slope of that line was out here like this. So this secant line here is closer to the slope of that tangent line. So it's a better approximation. So we would say 2.5 is a better approximation of the slope of that tangent line than it was when x equals 2. We could repeat this process and get an even better estimate for the slope of that tangent line. See, we're moving now this point a little bit closer to 1, 1. Now we're moving the x value to 1.2. And again, we would plug 1.2 into our function y equals x squared because that point is on the graph of x squared. So we can take our x value, plug it into our y value, and get the y value of 1.44. And again, we can calculate the slope of that secant line. Now the slope of this secant line is even closer to the slope of that tangent line when x was 1.5. When x was 1.5, we had a slope of 2.5. Now that x is at 1.2, when we did our slope calculation, we can see we get a slope of 2.2. Let's go ahead and create a table of values showing what we've done so far. We took the slope of our secant lines at these different values. So let's calculate those. We said when x was at 2, when we chose the value of x, created the secant line through the point 1, 1 and 2, 4, we found the slope of that secant line is 3. We moved the point a little bit closer to 1, 1. We chose 1.5, And we did the slope calculation when x was 1.5, and we got a slope of 2.5. And then we moved our x value a little bit closer to 1, which we moved our x value to 1.2. Then we did our slope calculation, and we got a slope of 2.2 for that secant line. Now, if we continued this on and calculated the slope of the secant lines for these different x values, we would get these values here. I think we can see if we let x be 1.0001, I think we would guess our slope of our secant line would be 2.0001. And if we continue that on, it appears that the slope of those secant lines is getting closer and closer and closer to the value of 2. Now, could we do the same thing from the other side? And what I mean by that is, could we choose values of x that are approaching 1 from the other side of x? So here, what we're doing now is we're going to choose a value of x here. See, we had the point 1, 1 here. When we did our calculations of the slope of the secant lines from 2 back to 1, we did a secant line, and we calculated that slope here. Then we calculated the slope between 1 and 1.5 and got this slope. Then we calculated the slope between 1 and 1.2 and got this slope. Now we're going to choose points on the other side, on the left side of 1. So if I chose this point, 0.5 here, and then I calculated the slope of this line, then I could find this slope here. And then we're going to choose 0.9, and my 0.5 was a little off, I see there, but 0.9 would be even closer to 1, so maybe it's right here. And again, this line is going to have a slope even closer to the slope of our tangent line there. So we're repeating the same process that we did over here. We were using values to the right of 1, but now here we're going to choose values to the left of 1 and let those values get closer to 1 from the left side. When we do this, we can see that now those secant lines are approaching 2 from the left side of 1. 1.5, 1.9, 1.99, 1.999. We can see if we continued this and we chose 0.9999, we would probably guess the slope of that secant line would be 1.9999. And now those values are getting closer and closer and closer. So it appears that these two calculations from the left and the right are squeezing the value of 2. So we're going to estimate that our slope of this tangent line is 2. And what does that mean? Well, if we look at this graph of y equals x squared, at the value when x equals 1, we have a tangent line that has a slope of 2. That means that's the instantaneous rate of change of this function at that point. That's a very powerful tool in calculus, finding instantaneous rates of change. Now let's look at the notation that we're going to use in these calculations. This is called a limit. Now let's discuss the different pieces of this expression that we have here. What we did a few minutes ago is we looked at finding the slope of a tangent line at a particular point. So we took this graph of y equals x squared, and we said we're going to try to find the slope of the tangent line to this graph at the point 1, 1, when x equals 1. Is And that's typically how we identify where we're going to find the slope of the tangent line, is giving just the x value. But I'm saying we're going to find the slope of the tangent line where x is 1 and y is 1. So let's take a look at this notation here. We have LIM is called the limit. That means the limit as q goes to p. Now, in our example, we're letting this point right here be p, and then we chose some arbitrary point out here. I'm just going to call this maybe just x. So if I label this particular point x, the y value, y, would just be the function, because if I just plug y in, well, for this function, what does y equal? Y equals x squared. So I can actually replace this y value with x squared, because that will give us our y value. Now this is the point we're calling Q. From these 2 points, we could draw in our secant line, and we were able to calculate the slope of this secant line. Now over here, this is representing the slope of our secant line. M represents, in mathematics, we let M represent the slope of a line, and then we have the subscript PQ. That indicates we're finding the slope of that secant line. So that's the notation right here. This right here is the slope of the secant line. So the limit of the slope of the secant line as Q approaches P. What we did on the previous slide was we let this point right here, this point Q, get closer and closer to P by bringing this point in here, then here, then here. Q is getting closer and closer to P. What happened when we took this value of Q and let it, the point Q, and let it approach the point P? Well, it got closer and closer to the slope of our tangent line. So this is the notation we use when we want to find the slope of the tangent line. We say the limit of the slope of the secant line, M subscript PQ, as Q approaches P equals the slope of our tangent line, M. So this is the notation that we will be using. Now let's take this a step further. Could we actually plug in the slope of that secant line? Well, we know we were calculating the slope of that secant line, so we can plug our values in. We know it's going to be the change in y over the change in x. We discussed that a few minutes ago. This is how you represent the change in y over the change in x. Well, the change in y, we said, is y sub 2 minus y sub 1, all divided by x sub 2 minus x sub 1. This is called our difference quotient. Now, let's write in our y sub 2 minus y sub 1. So our y sub 2 is simply x squared. Y over here is our x squared. That's our y sub 2. And y sub 1, in this case, is just 1. So we have x squared minus 1 divided by. Now, x sub 2 is just x, all divided by x sub 1, which is 1. And now, we could say, as Q approaches p. That's what we set up here. However, what else is happening? What's another way we could write this? Well, if we went over to our graph and took a look at what's happening over here, as q approaches p, let's take a look at what's happening to the x value. Well, the x value here, when we start, but then when we move a little bit closer, the x value goes to here. We move a little bit closer, the x value goes to here. We move a little bit closer, the x value goes to here. We move a little bit closer, the x value goes to here. So isn't x approaching 1? So we're going to write as x approaches 1. When we did the analysis on this, when we looked at the slope of that secant line as q approaches p, we said we think that the slope of that tangent line is 2, and that's correct. This is why the limit process, or limits, is so important in calculus. If we can identify how to do this right here and do this calculation, find this limit, if we know how to find this limit and we can come up with the answer too, well, we found a way to find the instantaneous rate of change of a function at a particular point. Only given that one point, we don't need 2 points. But we do need to know how to evaluate this limit before we can do this. So that's why limits are so important in calculus. It helps us find the information we're looking for. In general, we know that the slope of, let's just choose any arbitrary 2 points on this graph. We'll call the first x value just x sub 1. Now, when we find the y value, we would plug this x sub 1 value into the function. So it's very important to be comfortable with function notation, this f of x sub 1. That just means we're taking x sub 1 and plugging into the function to find our y value. Our second point we're going to label the same way. We're going to say that point is x sub 2, f of x sub 2. So in general, we can find the slope of this line, this secant line, with our slope formula. Our f of x sub 2 minus f of x sub 1, all divided by x sub 2 minus x sub 1. So that's how we will find the slope of a line. And in particular, we're finding the slope of these secant lines. That's what we've been practicing in our slides. Now, there's another way we can find the slope of that tangent line. We're going to use technology to help us do it a different way. What we're going to do is this. Let's take a look at our graphing calculator. Here on the graphing calculator, I have a circle graphed, and then I have a tangent line to that circle at the point when x equals 1. So I just plug those into my graphing calculator. Let me show you what that looks like, those equations. And then I just graphed those on my screen. Now, we're interested in finding the slope of this tangent line to the curve at x equals 1. So what I'm going to do is I'm going to use the zoom feature in the graphing calculator. So you can see here the zoom key. I want to zoom in at that point where we are tangent to the curve. So you can see the cursor is blinking at that point, so I'm just going to zoom in at that point. Now I'm going to zoom in again. Let's see what happens. So there's the circle, and there's the tangent line to the circle. Let's zoom in again. So it's harder and harder to distinguish the line and the circle. Let's zoom in again. So you can see it almost appears that the line and the circle are the same. I'm going to zoom in one more time. And it appears, there's the circle right there. It appears it's a straight line. We have zoomed in so many times that the graph actually looks like it's a straight line. That's the idea behind this other technique we're going to use. I'm zooming in one more time. Yep, I think it was off a little bit, but you can see the two lines actually look parallel, don't they? Now, the reason that it isn't tangent, I didn't move my cursor to the point of tangency, but you'll still get the idea. What we can do is we can zoom in to a graph at a particular point enough times and choose 2 points on that line now and calculate the slope of the tangent line at that point. So if I used my trace key, I hit trace and I moved up to the line. It jumped out of the picture, didn't it? So let me go back to the circle here. It's 0.98. And now I'll jump to the... Okay, if now we're on the line. So I could choose 2 points on the line, and I could do the calculation of the slope of that line over this very, very small interval, and it would be a good representation of the slope of the tangent line because we've zoomed in so many times. So that's the idea behind our new technique. So let's go back to our slides. So it says, find the slope of the tangent line at x equals 2. Use your calculator to zoom in at x equals 2. Here we have a function y equals, I believe this is 1/3 x squared. And we're trying to find the slope of the tangent line at x equals 2. What we're going to do is we're going to graph this in our graphing calculator and then choose the zoom feature and zoom in closer and closer until the line actually looks like, the function actually looks like it's a straight line at that point. Here I've done this with a computer generated graph. Here I've zoomed in around 2. I'm going to zoom in again, and you can see that's almost looking like a straight line. So if we zoomed in one more time, that looks like a straight line. And you can see the points around it are within 100, I mean, I have 1.98 to 2.02. So if we chose a point on each side of 2 and plugged it into our slope calculation, that would be a very good representation of the slope of the tangent line. So let's take a look at that. I didn't have that calculation down, so let's see if we can do that. Here we've zoomed in, and if we were able to go back to our graphing calculator. If we looked at the function now, we're going to clear these graphs out. And let's deselect this one so this one doesn't graph. And we'll deselect this one so that one doesn't graph. And we'll go back up and graph 1/3 x squared. So if we have 1/3 x squared, and then let's just look at a standard window. So I know we've been using the zoom feature, so I'll go back and just select 6 so we can get a standard window to graph. And now we're going to use our zoom feature again. So I'm going up to zoom, and we're going to zoom in, so I can select 2 or use the cursor to go down to number 2. And then I'm going to move the cursor over to, there is about x equals 2, and then I'm going to go up and touch the graph at that point, and then I'll hit enter. So it's zoomed in by a factor of 4. So let's move it over just a little bit more to where x equals 2, and then we'll go up to the graph, and then I'll hit enter again, and it will zoom in again. And if I zoomed in again, and then I'll zoom in one more time. And you can see it's giving us our x and y values, so we're very close to x equals 2. Let me move that over just a little bit. Okay, and then I'll move it down to the graph. So it will zoom in around x equals 2. It'll center it again around that value now. And now I'm going to hit trace. So now I can pick up 2 points on this line. I'm going to choose one point that's below x equals 2, so I could choose this value. I have an x and a y value now. And if I chose those 2 values, which is 1.9996 and 1.3328, that would be 1 point on the graph. And then I'm going to move up the graph, choose a point on the other side of 2, to the right side of 2. So let's choose this point right here. So that point is 2.0029, 1.3373. So if you used those 2 points to do your calculations for the slope of that tangent line, that would be a slope of a secant line, but that would be a pretty good estimate for the slope of the tangent line. So with your calculator, plug those values in, we would have 1.3373 minus 1.3328 divided by 2.0029 minus 1.9996. Now I don't have that calculation done, so let's take a look at that. 1.3373 minus 1.3328. That would be 0.0045. Let's squeeze that in. And then we'll take 2.0029 minus 1.9996, and you get 0.0033, and now we'll divide those. So we have 0.0045 divided by 0.0033. So when we do that calculation, we get 1.3636. And it's repeating. So this is the estimate for the slope of our tangent line when x equals 2. We would be saying this line here, this tangent line to the curve, has a slope of 1.3636. And if we looked at the graph and tried to determine if that seemed reasonable, it's up 1. That looks reasonable. If we just eyeball that, if we went up this much and looked at going back over, oops, does that seem reasonable? Calculation 1.36, and it does. Let's look at an application problem. Suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto 450 meters above the ground. Find the average velocity of the interval on the interval 2 seconds to 3 seconds. Find the velocity of the ball after 5 seconds. When a problem says after 5 seconds, it's meaning at 5 seconds, what is the velocity? So it's an instantaneous velocity. Now you'll notice the first part says find the average velocity. So we should be thinking to ourselves, average velocity is the slope of our secant line. So we would be looking at this calculation for the slope of our secant line. And you can see we have the 2 points where we're going to have to find the y values, but we could plug those in to our slope formula, and that would give us our average velocity. Now for the velocity at 5 seconds, that's our instantaneous velocity. We want to know the velocity at that instant. So that's the slope of the tangent line. So whenever we see an average velocity, we should be thinking slope of a secant line. When we want to find an instantaneous velocity, or the velocity at a particular point, that's the instantaneous velocity. Galileo found that the distance fallen by a freely falling body is proportional to the square of the time it has been falling. This is important to solving this problem. If the distance fallen after t seconds is denoted by s of t, so s of t represents how far the object has fallen in t seconds, then Galileo came up with this little formula to determine how far an object has fallen in a particular time. So this is what we're going to use to do our calculations. Now let's just take a look at this s of t just for a moment. Now we said the s of t represents the distance it has fallen. So does this make sense? If we plug 0 in for t, 0 seconds, well, it has fallen 0, a distance of 0 meters, which makes sense. Now if we plug t equals 1, the object would have fallen 4.9 meters in that first second. If we plugged in 2, we would have 4.9 times 2 squared, or times 4. So that would be something like 119.6, it looks like. So that's how far it has fallen in 2 seconds. So you can see it has fallen further in the second than it has in the first second, of course. It falls faster and faster and faster. Speaking of speed, so it's going to fall further in each subsequent second. For part A, we need to find the average velocity of the ball on an interval, but part B, we need to find the velocity at a single point. And that was the difference we were talking about earlier. Average velocity as opposed to instantaneous velocity, the velocity at a single point. We said to calculate our average velocity, we're going to use the slope of our secant line. If we looked at the slope of our secant line on the interval 2 to 3, now here's the graph we're going to be using, and if we looked at the secant between the 2 points 2 and 3, we could calculate the slope of this line. We know the t value in this case is 2. How could we find the y value? Or the s value in this case, because our function is written as s of t. S is going to represent the distance fallen. So we could just plug this in to our 4.9 t squared. We're saying at 2 seconds. So we're looking for s of 2 for 4.9 times 2 squared. So that's how we would find the y value. And I think I said that was, what is that, 19.6? I hope that's right. Now to find when x equals, or t equals 3, we could do the same thing. We could plug the value of 3 in and do our calculation here. So that's how we would calculate the slope of that secant line. And there's our calculation. There's our s of 3 minus s of 2 all over 3 minus 2. So we get 24.5 meters per second. That's the average velocity over that time interval. To find the instantaneous velocity, let's take a look at a table of values. We would go back to either finding the slope of the secant line as we choose values that get closer, because we're trying to find, let me draw to make this a little bit clearer. Our function is 4.9 t squared. We are trying to find instantaneous velocity, which means we're trying to find the velocity at that instant. Now the instantaneous velocity, we said, is represented by the slope of this tangent line. So what we're going to do is we're going to start by choosing a value out here, create the slope of that secant line through 5 and 6, and find the slope of that secant line. Then we're going to choose a point closer to 5. We'll go down to 5.1, find the slope of that secant line. Then we'll choose a point even closer. So these values are going to be getting closer and closer to the slope of the tangent line. This is just like the process we used a few moments ago. So here are the values that we would get by calculating the slope of those secant lines as t gets closer and closer and closer to 5. You can see we would get 49. It appears it's approaching 49. And our units would be meters per second. To find the instantaneous velocity. Now there was another way we could have done this. We could have graphed 4.9 t squared or x squared in our calculator, zoomed in when t equals 5, and then chosen 2 points from the slope of that very, very small tangent line that we created from zooming in so many times. So there's 2 different ways that we could have found this value. one last thing that I'd like to discuss. This is just a different form that we're going to be seeing quite frequently in the upcoming videos. It should be very familiar to you because we've been looking at this in our slides today here. We're just going to choose an arbitrary point A. We're going to try to find the slope of a tangent line at A. Now this is representing the Galileo's formula that we just used. 4.9a squared then would be the y value, because that was the function we were given. Our second point we're going to label as a plus h. So if we label this second point a plus h, the distance between these 2 points would just be h. We could label our second point a plus h, f of a plus h. Putting this into our slope formula, that would be the slope of our secant line. We would have y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. We would get this. Now we can simplify this expression a little bit. And you can see if we took now the limit as h goes to 0, look at our diagram. This distance between here and here is h. So if we let this distance, let's say that distance is, well, it looks like it's 1. At this point right here, h equals 1. Now if I move the point here, it looks like h equals 0.75. Now if I move the point here, h equals 0.5. If I move the point here, h equals 0.25. If I move the point here, maybe h equals 0.1. So we can see that as we move that point closer and closer, let's look back up here at our limit now, you can see h is going to 0. That's why we're saying in this limit, h is going to 0, because this distance down here is h. We're letting that point get closer and closer and closer to a, so h is going to 0. We know that this calculation right here will give us the slope of the tangent line at this point here. So this calculation here, if we knew how to do this, that would give us the slope of that tangent line. Well, we just looked at finding, we found that in the last slide. I believe it was 49.5. So we know the instantaneous velocity.